Without the laws of science and physics, there would be no point, jeté, pirouettes, lifts, leaps, or even fouettes. Today, I'm going to be breaking down the physics behind this one move, a fouette. First of all, you must be wondering, what even is a fouette? For starters, it is most definitely one of the hardest dance moves out there. A fouette, meaning whipped in French, is the motion of one turning, whipping their leg around, in which this movement allows them to do a continuous sequence of turns without stopping. Most commonly known from the Black Swan Ballet, in which the principal dancer does 32 consecutive turns. The simple scientific explanation of this turn is that one pushes off their foot and maintains rotation, resulting in friction between her shoe and the floor, and which reduces momentum. Before we get started, I'm going to talk about some key factors that are needed to know, such as torque, which is the tendency of a force to rotate a body, as it is demonstrated by the equation T equals Fd, d being the distance from the central axis, also known as the radius, and F being the net forces. Another factor includes angular velocity, which is how fast you can cover a given distance, as it is how fast you can get around an axis, known by the formula omega equals v divided by r. V is the velocity and r is the radius, and it is measured in degrees per minute rather than meters per second. Another factor includes momentum. There is two types, linear and angular. Both use the formula P equals mv, although angular momentum remains constant unless acted on by a torque. Unlike momentum, angular momentum does depend on where the origin is chosen, followed by rotational inertia, which is the body's resistance to a rotational motion, as it increases when more mass is distributed further away from the axis of rotation and decreases when the mass is distributed closer to the axis of rotation. Inertia is about a mass, rotational inertia is about a size, more specifically, the radius. It is demonstrated by the formula L equals mr squared for a circle or cylinder or body approximating a cylinder. The next factor is friction, which is needed, but it is crucial that the necessary amount is applied in needed times or in order to be successful. Too much friction is also bad in ballet. For example, when a dancer is doing a pirouette, there is friction between her foot and the floor, which stops her from spinning too fast or losing control and falling. However, if there is too little friction, for example, if the floor and the dancer's shoe are very slippery, then the dancer is unable to maintain a grip on the floor and she will slip over or spin too fast, losing control of her turn and falling over. Followed by the center of mass of a human. When a system is balanced around its center of mass, it is said to be in the state of equilibrium. The center of mass can be referred to as a pivot point, which is where the axis touches the floor, around which is a system that can revolve. The system revolves due to the rotational equivalence of force, known as torques, which rotate the system. Although the center of mass depends on each person's weight distribution, as well as varies between male and female, although it is typically found 10 centimeters lower than the navel, near the top of the hip bones. After speaking with several professionals, here's what they had to say in what makes a perfect fouette.
I would say a perfect fouette includes having a really strong center core to have lots of balance when you're turning and be able to pull up with your releve so that you have nice momentum going up into the air, and the use of your arms will make for a lot of momentum when you're turning around.
I think the perfect fouette needs a good sense of balance, someone who has no fear, to be able to turn quickly, I think are really important. I think also it needs a lot of time and effort put in the dance studio in order to be able to perfect your fouettes. Lots of time and many years of training.
Now, taking what we learned, let's apply it to reality. When performing this move, it is crucial that you're on the top of the block, also known as the top of your dance shoe. This is so that it aligns with your vertical axis, allowing you to stay balanced, resulting in the mass being directly above the area of support. Although to stay balanced, you have to constantly reconfigure your body by pushing into the ground in specific ways at specific times, making sure her center of mass stays above her foot, as the force exerted is not greater than the force of gravity, but is just enough to push her back on the top of her block. The center of gravity must overcome the centripetal force, which is the force that draws the body away from the center of rotation, allowing her to keep her arms and legs in a compact position and above so torque is unaffected. In a fouette, your foot flattens and twists as it rises back up onto point, pushing the floor to generate another small amount of torque as arms sweep open to keep her balance. This last term is an example of when one does not apply the correct usage of her center of mass, resulting in unsuccessful turns. The following term is an example of when one extends their leg for an extended period of time. When doing so, the more momentum it stores, therefore resulting in more momentum it can return to the body, meaning more angular momentum, and that she can be more efficient with her leg extend ratio before needing to replenish the lost momentum that was taken via friction. Here's an example of a fouette when she extends her leg for a longer period of time. Nextly, let's take into account impulse, and more specifically, pliés. The deepest plie supporting the greatest force in the allotted time, resulting in the greatest impulse, as there is a greater force applied for a longer amount of time. With application of the prior information one presented, one determined by bringing arms closer to the body after extending the leg, one can be more successful, due to the fact that all turns are governed by angular momentum, which is angular velocity times rotational inertia. Except for what's lost in friction, the angular momentum has to stay constant while the dancer is on point, also known as the conservation of angular momentum. Therefore, when she brings in her arms closer to her body, inertia decreases. In order to conserve angular momentum, the velocity, also known as the speed of her turn, has to increase, allowing the same amount of stored momentum to guide her through the sequence of multiple turns, also seen by ice skaters, which draw on their arms and legs to go faster and faster. As a dancer, I've always wondered, why can you turn faster in some shoes than others? Well, that is due to the coefficient of kinetic friction. When calculating, it is crucial that you utilize a clean work surface so no dust particles affect the friction once calculating. Each floor has a different coefficient, and in combination with different types of dance shoes, there are numerous combinations, explaining why it's easier to turn in some shoes rather than others. This plays a big role in the efficiency of your turns. As you may have noticed, when breaking it all down, none of these turns have been successful. That is because it takes a balance of these four things: making sure you're over top of the center of your mass, as well as extending your leg for a long period of time, bringing your arms in close to your body, and deep pliés. These four things are the fundamentals of fouettes, and when unbalanced, this is a formula for failure.